Good day, everyone. We are from the Department of Statistics of the CUHK. Today, we will continue our fascinating journey into the world of calculus by introducing the number e. Firstly, let's begin with the first section of our presentation, proof that the definition of e is a valid definition. In the previous chapter, we defined the Euler number e as a limit, e equals limit as n approaches infinity of 1 plus 1 over n raised to the power of n for n equals 1, 2, 3 and so on. But how do we know that this is indeed a valid definition? How can we be sure that limit as n approaches infinity of 1 plus 1 over n raised to the power of n exists? This was, of course, strongly indicated by the trial calculations we did for some values of n, but absolute certainty requires a mathematically valid proof. In our proof, we will make use of the familiar binomial theorem, a plus b raised to the power of n equals sigma from k equals 0 to n of n. Choose k times a raised to the power of n minus k times b raised to the power of k, where for k greater than or equal to 1 n choose k equals n times n minus 1. Times and so on times n minus k plus 1 divided by k factorial, where k factorial equals 1 times 2 times and so on times k is called the factorial of k. As a special case we define n choose 0 equals 1. The numbers n choose k are called binomial coefficients and they appear in Pascal's triangle. The binomial theorem can be proved by mathematical induction. But what does this have to do with our definition of e? Well, the proof that the sequence x sub n equals 1 plus 1 over n raised to the power of n converges is based on a property of R, the set of real numbers known as the completeness axiom for real numbers. By this axiom, let x sub n be a sequence of real numbers with the following two properties: x sub n is increasing, that is x sub n is less than or equal to x sub n plus 1 for all n, x sub n is bounded above. That is, there is a real number u such that x sub n is less than or equal to u for all n. Then the sequence x sub n converges and its limit is a real number. The completeness axiom states that every increasing sequence of reals, which is bounded above, converges towards a real number. By contrast, it should be noted that the set Q of rational numbers is not complete in this sense. One can easily find examples of increasing sequences of rational numbers which are bounded above but do not have a rational limit. It now suffices to prove that the sequence x sub n equals 1 plus 1 over n raised to the power of n has the two properties stated in the completeness axiom. This is done in two lemmas. Lemma 2 states that the sequence x sub n equals 1 plus 1 over n raised to the power of n is increasing, that is x sub n is less than or equal to x sub n plus 1 for all n. And lemma 3 states that the sequence x sub n equals 1 plus 1 over n raised to the power of n is bounded above. To prove lemma 2, we use the binomial theorem to expand x sub n equals 1 plus 1 over n raised to the power of n, and x sub n plus 1 equals 1 plus 1 over n plus 1 raised to n plus 1. Refer to the process of expanding x sub n and x sub n plus 1 on screen. When comparing these two expansions, we observe that both consist of positive terms. The two first terms are the same. From the third term onwards, every term in the first expansion is smaller than the corresponding term in the second expansion because 1 minus k over n is less than 1 minus k over n plus 1. The latter expansion contains one extra term at the end having no counterpart in the first expansion. Therefore we conclude that x sub n is less than x sub n plus 1. Lemma 3 states that the sequence x sub n equals 1 plus 1 over n raised to the power of n is bounded above. We will prove that x sub n is less than 3 for all n. From the expansion of x sub n in the preceding proof we see because 1 minus k over n is less than 1 that x sub n is less than 1 plus 1 plus half factorial plus and so on plus 1 over n factorial. But the right-hand side can be estimated above by geometric sums as follows. Therefore, we have x sub n is less than 3. This concludes our discussion on proof that the definition of e is a valid definition. The next section discusses an alternative definition of e. Consider the sequence of numbers y sub n defined by y sub n equals 1 plus 1 over 2 factorial plus and so on plus 1 over n factorial. The sequence y sub n is clearly increasing. Furthermore, in proof of lemma 3 we showed in fact that y sub n is less than 3 for all n, hence y sub n is convergent. The simplified binomial expansion of x sub n equals 1 plus 1 over n raised to the power of n strongly suggests that limit as n approaches infinity of y sub n equals limit as n approaches infinity of x sub n equals e. Indeed, the sequence y sub n converges very much faster towards e than x sub n. In the table below we have calculated the approximate values of the ratio of errors for some values of n, as we have previously proven that the limit of the expression 1 plus 1 over n raised to the power of n s n approaches infinity is equal to e. We can show that it is also equal to the limit as n approaches infinity of the sum from n equals 0 to infinity of 1 over n factorial. Now, let me discuss some notes on this alternative definition. If we pick any ratio between 0 and 1, there are only finitely many values of n, for which n over n is not greater than r. However, since n goes to infinity, the proportion of pairs of n, 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 n that are smaller than Rebecom's increasingly small. Therefore, the average proportion of pairs of n, 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 n tends to 1 as n increases. In conclusion, we have presented an alternative definition of e based on the limit of a sequence of numbers. This alternative definition is equivalent to the standard definition of e and has important properties that make it useful for mathematical calculations. The next section discusses the exponential function. The paramount mathematical importance of the Euler's number e derives mostly from the rich variety of nice properties possessed by the e-based exponential function f x equals e raised to x. Lemma 5 states that for all real numbers x we have e raised to x equals limit as n approaches infinity of 1 plus x over n raised to the power of n. This can be proven by showing that limit as n approaches infinity of 1 plus x over n raised to the power of n equals limit as n approaches infinity of 1 plus 1 over n over x raised to n over x raised to x equals e raised to x, because the expression in the square brackets converges to e. As for e itself, we can also give an alternative, and much more useful, definition for e raised to x in terms of an infinite sum, a power series. Lemma 6 states that for all real numbers x we have e raised to x equals 1 plus x squared over 2 factorial plus and so on equals sigma from k equals 0 to infinity of x raised to k over k factorial. Justification: analogously to the proof of lemmas 2 and 4, we again apply the binomial theorem to expand the power 1 plus x over n raised to n. The derivation is nearly identical. This concludes our discussion on the exponential function and introduction to e. Thank you for your attention.